Welcome. Now in this video we're going to introduce the electron spin. So first we're going to talk about why we need it, and we will discuss the structure of how it works quantum mechanically. And then in the next videos we'll talk about the consequences it has on spectra. So if you remember back to the last video, we closed by mentioning that P to S transitions actually show up as doublets. And this should have been surprising because what we derived in class is that there should actually only be one P to S energy, right? So there's just one energy allowed for P states, one energy allowed for S states of a given value or given values of N. And so these should show up as singlets without magnetic fields. And so this tells us that we are missing something in our theory, right? If we get qualitatively different results, we're measuring a doublet instead of a singlet that is different in kind, not just a little quibble with the numbers, then it means that we are missing something fundamental in our theory in the first place. All right, so shown on the left here is an example of the measured lines you'd see in a hydrogen spectrum, whereas you would expect this to find just one line right at this first peak in the Balmer series. If you really zoom in, you do really high quality experiments, then you can in fact see two lines that are separated by just the tiniest bit, but it is measurable, even if it is small. And a solution to this was proposed by Wolfgang Pauli in a really ad hoc way. So he really just said, look, we could solve this problem, or we could explain this discrepancy if we just assumed that electrons have this extra thing called spin. So really what Pauli said was that there is some other degree of freedom besides just the principal quantum number, the angular momentum quantum number, and the magnetic M sub L quantum number. There is some other quantum number that this thing seems to experience, and the way that this interacts with everything else in the atom, it almost behaves as though we're sort of spinning in space. And what we mean by spin is really we just mean that the electron has an inherent angular momentum. That has nothing to do with the orbit that it's in. It has nothing to do with whether it's in an S shell or P shell or so on. It just has its own angular momentum, almost as though it were spinning in space. So this is not what Pauli actually suggested. The viewpoint is not that electrons are physically spinning or rotating in space, but the way that this looks, you would see something similar coming out of the math if you derived it as though it were a ball with a particular charge on its surface spinning in space. And so this is where it comes from, and the name for spin has kind of stuck. But really what it means is that it's an inherent angular momentum. And because it's an inherent angular momentum, it actually will follow a lot of the same rules for the angular momentum. So why don't we compare some of those previous rules real quick. Right, so when we talked about just angular momentum eigenstates, we could write them in Brockett notation using two quantum numbers, L and M sub L. And what this means is that if you apply L squared onto this state, L M sub L, this has an eigenvalue of h squared L times L plus 1 times the original function. And similarly, this is also an eigenfunction of Lz, which is the angular momentum projected onto the z-axis. So this is Lz applied to M sub L is equal to h bar M sub L times L M sub L. And also what we know is that L can take allowed values from 0, 1, and so on up to infinity. And M sub L, the allowed values for M sub L depends on L, and they go from minus L plus 1, and so on up until you get to L. So spin is an angular momentum, and so it needs to have the same basic structure as angular momentum. And so I can be a bit more specific about that by just giving you some notation and showing you that the same things end up holding. So in analogy to orbital angular momentum, we will write in bracket notation that says S and then m sub s, and then we have really similar operators all along. So we have an s squared operator, which is the total spin, just like L squared is the total angular momentum. And if you apply s squared onto s m sub s, then what you should get is h bar squared s times s plus 1. We similarly have an sz, which we can apply into this, and what we get back is h bar times m sub s times the ket. Sorry, this up here should be m sub s. Okay, so this structure is the same, but now the major difference is that for the spin of an electron, s can only be 1/2. It only takes one value. If we take that s can only be 1/2, and we apply the same logic from the angular momentum part, that tells us that m sub s can only be, right, so the first value allowed is minus 1/2, and then if we add 1 to that, we get 1/2, which is now equal to plus s, and so that means that there are only 2 possible values for m sub s. Okay, so what does this mean? So this means that spin and orbitals, and orbital angular momentum, so the s and m sub s versus L and m sub L, have the same basic structure, right? They have the same common themes in terms of how the eigenvalues look. Also, their degeneracies, right? So there are 2 states. And the same token, for orbital angular momentum, the degeneracy for a state with quantum number L, the degeneracy of that state is 2L plus 1. So if you plugged in S to 2S plus 1, you'd get 2. So let me make this a little bit more explicit. Degeneracy G sub L, in this case, is 2 times L plus 1. And the degeneracy G sub S is still 2S plus 1. Okay, but now the major difference is that whereas for orbital angular momentum, you can have infinitely many different L values, and they are all integer. For spins, for the spin of a single electron anyways, the only allowable S value is 1/2, right? So not only is it non-integer, but it's also only one possible value. And so that means that you can have an electron basically either spinning up or down, right? So either ms is up or ms faces down. And that basically means we have 2 possible states we should consider. So one is the s equals 1/2, and then ms equals plus 1/2. And this is given a spin label alpha by convention, and is also referred to as spin up. And the other possibility is we still have s equals 1/2. That's the only possible value for s. But now we have ms is equal to minus 1/2. And these are called beta spins, and also referred to as spin down. So if we look at what happens with the application of s squared and sz onto these 2 different kets, so the alpha and the beta, or the spin up and the spin down kets, so we see something really straightforward. So for example, if we apply s squared onto alpha, right, going back to this equation up here, this would be h bar squared times 1/2 times 1/2 plus 1. So this should be 1/2 times 3/2, or 3/4. And so s squared onto alpha equals h bar squared times 3/4 times alpha. And similarly, applying sz onto alpha should just give us plus h bar over 2 on alpha. Whereas on the other hand, if we apply s squared onto beta, we see, again, h bar squared 3/4 times beta. And when we apply SZ now, this is the only one that's different, so applying SZ onto beta, we get minus h bar over 2 times beta. So now we've stuck with writing these as Brockett notations because these are purely quantum objects. Okay, so you can look at the structure and maybe think to yourself that maybe MS would look something like the equivalent of the spherical harmonic with S and MS. But the spherical harmonics are only defined when these are integers, when this bottom one is an integer. So furthermore, spherical harmonics are functions of the angular coordinates when you're in spherical coordinates. But this is an intrinsic quantity of the electron, so there's no way to describe this in terms of other external, somewhat classical looking objects, because spin is a purely quantum object. And so because spin is purely quantum, we were sticking with writing this in terms of eigenkets, because there's really no classical equivalent. There's no way to really write this as a function because it's not a function. It's this weird extra degree of freedom that only has two possibilities. And so instead of trying to turn this backwards and turn this into something like a function, we're just going to stick with writing in Brockett. And so what this means now is that we have two different possibilities for any spin vector. So we have alpha and beta, and then we'll choose these alpha and beta kets. We'll make them into a basis by choosing that they are normalized and that they are orthogonal. And here's what I mean by that. So the inner product of these two alphas is equal to 1. The inner product of betas is equal to 1. And the mixed inner product is always 0. Okay, so this lets you define essentially a basis for any spin that a particle could have. All right, or we can write this equivalently. In the angular momentum-like way as this. Okay, so now let's talk about how this applies to the hydrogen atom. So it turns out that the spin has a very small effect on the total energies for the hydrogen atom, although it will play a part in the spectra. And so what that means is that we can basically just tack on the spin degree of freedom to the existing eigenstates that we already had. So let me be a little bit more specific. So for example, we've been writing eigenstates with 3 quantum numbers like this. And now what we're gonna do is just tack on one more quantum number. Right? We're not bothering with the S quantum number because that's redundant. We know that will always be 1/2. Okay, and this we write as N L M sub L M sub S. And this is a function of R theta phi. And then what we do to signify that we're talking about a specific spin is we need to add one more function, and we add this somewhat fictitious function sigma, which is really just a bookkeeping device so that we can keep track of the fact that we are including the spin in the definition of this wave function. And writing out explicitly now, we would have a radial equation, a spherical harmonic, and now we're just going to stick with writing this still in terms of a ket, so this sigma ket. So as a final example, this means that we would now equivalently have two different solutions with the same N, L, and M sub L. These will be plus 1/2, which is equal to the radial part, the same radial part, the same spherical harmonic, and then times the alpha spin function for the spin up spin function. And then we have this spin down version, minus 1/2 now for MS. And this still has the same radial equation, the same spherical harmonic, but just a different spin function. Okay, so this is now two solutions with the same r, theta, and phi dependence, but they just differ in terms of this extra degree of freedom that we call spin. The last point of interest I want to mention is that spin was proposed as a solution to this problem by Pauli as just another one of these like ways to fill a hole, but with no real formal justification. He didn't necessarily believe that that was what the result was going to be. And it wasn't until many years later that actually Paul Dirac came up with an explanation for the origin of spin by deriving the equivalent of the Schrödinger equation, but for relativistic theory. So Paul Dirac basically combined relativity with quantum theory at the time, and spin came out naturally as a result of that. But it's actually quite a bit more interesting than that. So Paul Dirac's theory has also sometimes been referred to as four-component theory. And the four components fall out naturally from the mathematics. And part of what makes this really powerful is that two of these components are the normal spin. So you can think of it as alpha and beta, more or less. But the other two components are the part that makes this really challenging to think about. And the other two components are the antiparticles. And the other two components are the equivalent of alpha and beta, not for electrons, but for positrons, for the antiparticle of electrons, right? And so this is kind of wild. It means that the only way to rigorously derive the existence of spin, of the spin degree of freedom within quantum mechanics, is to go all the way to relativistic theory, so that it also gives you these antiparticles, which is kind of mind-blowing, right? There is no really rigorous way to go in between. And so in chemistry, when we talk about the spin, we're really just tacking on this extra degree of freedom into our non-relativistic theory, because that is a lot easier to do than to try to think about the actions of these positrons and everything else. And so that's the real origin for why we have to rely on this ad hoc definition of the spin, is because so doing that is much simpler than trying to deal directly with this Dirac equation. Okay, so this tells you a little bit about what spin is in quantum mechanics, a little bit about what spin isn't, and now in the next video we'll talk about how spin can interact with orbital angular momentum, and it gives rise to splittings that you can measure in spectra.